In this video, we'll be going over the cost function. The cost function is an algorithm that tells us how well our model is doing so that we can try to get it to do better. So going back to linear regression, we represented our model as y hat superscript I is equal to f subscript w comma b of x superscript I. And our model is predicting y hat based on the input x superscript I with the parameters w comma b. And we can rewrite it as this right here. And this is the same thing, just expanded. So what we want to do is find w comma b such that y hat I is close to y superscript I for all x superscript I comma y superscript I. And this makes intuitive sense, right? We want a model that basically predicts y hat, right? It predicts an output that is as close as possible to the actual output, right? Y superscript I. This means that if we can predict these data points correct, it will most likely predict new data points correctly. And how we can really decide how well our model is doing is by using an algorithm called the cost function. Okay? And like I said, the cost function compares the values of y hat and y. So we basically use the cost function as an error function. We're computing the error of our model. And so it starts off with this y hat superscript I minus y superscript I. And this is just the difference. It's just a difference between y hat and y. And what the cost function will do is square this value. And we want to compute the error for all data points within a training set. So we're going to use summation notation here. So we're going to go from I equals 1 to m, meaning that we're going to loop through every data point. And we want to find the average error. So we're going to divide by the amount of data points. So we'll multiply this by 1 over m. And by convention, we have to divide this by 2. This makes some of the simplifying easier. And this is the cost function. So we'll represent this as j of w comma b. And this is basically saying, hey, j is a cost function, and it uses the parameters w and b to compute this. And we can rewrite this as j of w comma b is equal to 1 over 2m times summation of I equals 1 to m of f subscript w comma b x superscript I minus y superscript I squared. So I just expanded y hat here. And what I now want to explain to you really is what the cost function is. So our overall goal with machine learning is to basically find values of w and b, right? And these values of w and b make up our model, right? And we want to find these values of w and b that make the cost function small. If we minimize the cost function, that means the error of our model is small, and therefore our model is doing pretty well in predicting outputs. So what we'll do here is visually compare the difference between our model, right? So let's say a linear regression model in this case, and the cost function. And we'll represent this as f subscript w of x is equal to w times x. So all I did here is just get rid of the b parameter. There's just a w parameter in this case. So we are going to compare graphs of the cost function and our linear regression model. So on the left side, we'll have our model, subscript w of x for fixed, it's a function of x. On the right side, we'll have our cost function. This is what we just worked with. It's going to be j of w. So on the left-hand side, we have a function of w. All right, so I'll make a graph right here, and this represents our data points. So x is on the x-axis here, so I have 1, 2, 1, 2, 3. And say our data points are these ones right here. So we want to find values of w that minimize our cost function, right? And we want to basically make our model predict puts correctly, right? So say we have a w value of 1. So we're going to let w equal 1. W equals 1, right? We said we're going to represent this function as wx. So basically we're going to represent our linear regression model as 1 times x, which is just x. And as you can see here, that's model the data pretty well, right? With almost no error. So if we plot this right-hand side as our cost function, so on the x-axis we'll have the values of w, right? So when w equals 1 right here, we see that our error is 0. Our error is 0. And when our error is 0, that means our cost function is 0, right? So we're going to plot this right here. When w equals 1, right, our cost function is 0. But say we chose a different value of w. Say we chose 0.5. If we chose a value of 0.5, our linear regression model would look something like this, right? It wouldn't model our data very well, right? You can see it underestimates it. And for this one, we're going to have w equals 0.5. We'll use our cost function to calculate the cost, right? So remember, we're going to say j of 0.5, so the cost of 0.5 is equal to, well, we're going to loop over the differences squared, right? So we're going to go, this predicts 0.5. Here, this is 0.5. So it's going to be y hat minus y, so 0.5 minus the actual value, which is 1, minus 1 squared. And we're going to go through each value. Remember we said we're going to multiply this by 1 over 2m, and m is the amount of data points. And in this case, the amount of data points is 3. So it's going to be times 1 over 6. And this computes to around approximately 0.58. So we'll plot this data point now on the right-hand side, the cost function. So when we have a w of 0.5, that cost was 0.58. Now say we're going to say w is equal to 0. Well, when w equals 0, our linear regression model is just a straight line, right? That makes sense. It's just basically y equals 0, right? And this basically models our data even worse, right? You can see how far it underestimates it. And now we'll compute the cost function for equals 0. This is going to compute to around 2.3. So you can see that the cost function is even greater here. So when our w value is 0, our cost is 2.3. So you can see it did substantially worse. And if you were to choose other values of w, right? Say you had a w of maybe 2, it would look something like that, right? And you compute the cost. You'll find that for all these values of w, if you plot the cost, you'll get a quadratic shape. It'll look something like this. And you can see that as the values of w get farther away from 1, the cost function is greater, meaning we have more error in our model. So obviously, a w value of 1 is going to be most optimal here, right? Because we've minimized the cost function. We've minimized the error of our model. So that means our model is doing well, right? A w value of 1 equals a good model because we have no error. But we really want to see how we can minimize this cost function, right? We just talked about, oh, we'll plug in values of w and see which values of w uses the minimum cost, right? But there's an algorithm to do this. So in the next video, we'll talk about gradient descent, which is used to find this point right here that minimizes the cost function. But that's our next video. I'll see you guys next time.